Okay, thank you everybody for joining us for our second presentation of the day. Our topic is Google Colaboratory and Python, Deep Learning Basics for CV Tasks by Kristina Host.
Thank you for the introduction.
You're welcome.
Okay, hi everyone. My name is Kristina Host, and today I will cover the topic of Google Colaboratory and Python. What are the deep learning basics for computer vision task? So we will do some introduction to Google Colaboratory, some Python basics for images, and then we will create a convolutional neural network. So I'm a PhD student and research assistant at the Faculty of Informatics and Digital Technology at the University of Rijeka, and I'm working in the domain of machine learning and computer vision, and my focus is on automatic recognition of human actions and activity in the sport domain. My focus is on handball, but we are doing different sports on our projects. So if somebody is interested in that part, let me know so we can maybe collaborate and similar. So that's about me, and now let's start about the tutorial. So first of all, we will do some introduction to Google Colaboratory, how to create a new interactive notebook, how to connect to a virtual machine, enter text, some commands, system commands, Python code, and similar. Then we will do some Python basics for images, just to get familiar with the environment. And after that, we will cover the convolutional neural networks on one example with the CIFAR-10 datasets. We will cover how to create a model, what are the basics terms that we need to know to implement it, how to train a model, and how to test a model. We will work with two libraries that allow us to train large neural networks, and their calculation are distributed to GPU servers. Because of that, we are using Google Colaboratory because it's a free Google platform that offers Jupyter Notebook virtual environment. The only thing that you need to have is the Google account. I hope everybody does have it. And once you sign in, you can use the GPUs and write your Python code. So you can use it in your browser, and the GPUs are free of charge. You can use CPU if you want, when you are not using neural networks or something that you need more power. You can change this in the runtime in Google Colab. We will pass through that, and then select that you are using Python and that you want to use GPUs. And then you will run the code that, for example, we took some hours with CPU. It will be in a few minutes for our cases. Okay, maybe we can get familiar with Google Colaboratory. You can open your browser and write Google Colab. Then you click on the link and click then on Open Colab. I'm already logged in, but you can log in. I will wait. Okay. I hope you managed it. So once you open Google Colab, you can here see some examples that are written for you, and you can use them and get familiar with Google Colab. You can use some recent file that you uploaded. You can connect to your Google Drive and upload everything that you have there. You can put codes from GitHub here and then use it and run it and everything, or you can upload something from your computer. First, we will create a new notebook just to see how it looks like. So here you can write the title of your script. Here you create a new notebook, rename, you can download this here. You can save a copy in Drive if you want to change something and similar, rename and other. What is important for us is to go to runtime and change runtime type to be Python and to use GPUs. Then when we will connect, we can work with it. Here are the files that you, for example, upload, or you can see here like the content if you add some titles and similar. So it's called a notebook because you can add code and you can add text. For example, you can click on this to add, or you can put your mouse between two fields and then add what you want. For example, if you want to write a title, you will press this, and then in the table of content, it will appear. For example, if you want it to be of second level, you will write like 2 hashtags in front of it. Or press more time and then it will appear. So this is like how you add some text. You can also add links, pictures. You can manage how the text would look like. It's like really interactive and you can use it. Okay, so this is like how to create a new notebook, but today we will use the notebook I prepared for you. So in the chat, you have the link to the drive with the materials that we will use today. So please, everybody open them. So you have the presentation. Here you have the working script on which we will work on, but later when we finished, I will also put the entire script everything that we have written today. Please download this map or just these 3 files on your computer. So you need the script and you need these 2 images. I will give you a few minutes. So the link is in the chat, and please then download the script and the image of a book and this image called life. And then we can start with the script. Okay, so we are in Google Colab. We go to
Sorry
File
for
and
interrupting. We have a raised hand. Yeah, the person that raised the hand left, so I'm not sure they raise the hand again. I'll give them availability to talk. You can continue, and I'll watch if they raise their hands again.
hear you. Can you hear me?
Yes.
Okay, can you repeat what's the problem?
Yeah, no problem. Somebody raised their hand, but they left the presentation. So if they join again and they ask to talk, I will give them permission. Maybe they had a question or something. So yeah, you can continue now. Everything is okay.
Okay, thank you. Okay, so I hope everybody downloaded the materials. Go to File and then Upload Notebook. You browse and then upload this working script that you have in your materials. Okay, so you see here that we have different titles. And if you press in the table of contents, you can see every title that we have that is there is a navigation bar that you can click on a title and then you will go through that part. So this is why it's interactive and for me really useful. Okay, so we will start with the introduction to Google Colaboratory. I showed you how to write some text, but the important thing is how to write the code. Please go to runtime. Go to runtime, change runtime type, and select the GPUs and save it. Once you did that, click this connect. Okay, when it's connected, you will get this tick here. These hashtags represent a comment. So this is a comment. In every place that I put this hashtag, we have to write some code. So this is the idea. If you Google Colab has a lot of libraries installed in the environment, but if you need to install anything else, it's useful to know how to write a system command, how it's the same thing when you are writing it on your computer, but here you just have to put the exclamation mark in front of it, and then, I don't know, pip install and what you want to install. Let's just check with system command which version of Python we are using. For example, to see how it performs. So we have to put this exclamation mark in front if we want to use a system command. And when we use Python commands, to run the code, you click on this play sign in front, or you can go to runtime and run all, run before the selected cell and similar. If you want to write Python code, then you write like normally. You don't have to put anything in front. So for example, a equals to 10, and we want to b equals to 20, for example, and then we want to sum these two numbers. We just write a plus b, and then we run the code and we obtain the result. This is the Google product. So we can connect with Google Drive, and you can easily do that and then retrieve files from your drive or save them to it. So it's useful to know how to connect with your Google Drive. We will not use it today, but I will show you so you can use it in other occasions. So you have different methods. You can just click on this button and then you can connect to it. Or you can do it by code that you can find in the code snippets. So Google Colab has this thing called code snippets where you can find some code that is easily to put in your script. For example, don't know, dry. So you have this mounting Google Drive in your virtual machine. How to do it? You can downloading files or import from Google Drive. So you have here the codes for that part. It's called code snippets. Okay, so let's try to connect to your drive. Run the cell to connect to your drive. And you have to permit this notebook to access your Google Drive. And then select the account you want to use. Agree to everything. And once it's connected, it will appear here in the files. So you have here the drive and everything that you have on the drive connected. If you need, for example, I don't know, address of something, you can copy the path and then do something with the images or what you want. Okay, so this is if you need something from your Google Drive. But you can also just upload to the files to the session, but you need to know that once the session finished, the files that you have in the session will disappear. So it's better to connect to a drive and save your progress on the drive and in any change that you did, because in the session you will not have this data after. Okay, so let's try to upload the files to the session. So you click on this upload to session storage and select the book and the live pictures. So you have also the warning that says that. So the files will be deleted when the runtime is like terminated. Once you put them on in the environment, you will see them here. I hope I'm not going too fast. Okay. For those that are not familiar maybe with Python, to import some libraries that we want to use and some functions, we write this code like import and then the name of the library, how it's saved. We will use OpenCV, that is CV2. His name is CV2. And we will use, for now, to show the images from Google Colab patches, this function for visualizing the image, because for some reason in Google Colab, this feature of OpenCV is not working. Okay, so maybe first of all, we can, after like importing the libraries that we need, we can load the images into the environment. So we just like uploaded here, but we have to work with them. So we will make two variables. The first one, it will be called book. And we will read the image with OpenCV. And we will put here the path to the image. So copy the path. So you go on the file you need, go to the three dots, and then copy the path. We will define another one. We will call it live. And we will also read the image and put the path inside. When we want to add some more code, we like go in the middle of the screen and then add some code. Okay, we will run this part. And now we have uploaded and read it, saved these images on the value of the images on the variable book and live, and now we can access it. So for example, we can see what is the shape of the image. Okay, so the live image is a bigger one and the book is a smaller image. With this function, we can visualize these images. So you can copy this part. and right. The first variable is life. And this is our image that we will work with. I will clear the output so you can see the code. And we will also show the book image. Okay, so let's make some change on the image. For example, we can get the value of the pixel on the position 100, 100 in the book image, and then change its color, for example. So we can write book. If you want to access some pixels, then you open the square brackets. And we can see which are the values. So maybe we can also show what is inside the variable book, show data. So we have zeros and other numbers, still 225 for every pixel. So it saved like a colored picture. So we have 3 dimensions. So we have 3 different columns for every pixels, for every pixel. Okay, so in this pixel 100, 100, we have this value for the blue pixel, the green pixel, and the red pixel. If you want, for example, change that part that this pixel, for example, is red, then we can change the values to this. And now this pixel will change his color. We can show the image. This pixel is really small, so you have to like look a lot to see it, but you can see that now here is a red dot. If we want to change more pixels, for example, in the life variable, to put, for example, the book image in the life image. So we can change, for example, from the pixel 50 to 275, and then from 950 to 1175 to now be the value of the book. Now we can check how the image looks like. So we have added this book inside our image. Why are we doing this? Is to see that you can change your pictures. And why is this important? Because neural networks are need a lot of data to train. And any modification you do on the images can be some data augmentation, and you can increase your samples with these procedures. For example, you can modify the height, the width, and you can rotate, you can change colors, you can blur the image and similar. We can run this part. For example, we want the image to be 3 times smaller in height and 2 times like bigger in width. And we want to change it in gray, for example. We can run this code. And now we like obtained a different one. So it's good if you, for example, work with images to enlarge your data set with some data augmentation in a way that you like make some modification on your images. For example, but you have also you have to think if it's like appropriate or not. If you have a person, you will not like rotate it in this way because the detector will not perform well because it's like it learns that the head is like on the top and stuff like that. Okay, you can save the change data like with imWrite. So with imRead, we like loaded the image in the environment, and with write we like save it where we want. If you want to save it on your drive, just change the path to your drive then. You can also blur the images and similar. Okay, this is the first part of the tutorial, is like to get familiar with Python. And now we will discuss the convolutional neural networks. I will give you a few minutes to run the code if you didn't. And then we will go to the other part of the lecture. Okay. Okay, in machine learning, we have unsupervised and supervised learning. When we work with supervised learning, we have labels about our data that we are working on with. For example, one of the most famous data set that are used for classification, which is one of the supervised learning, machine learning approaches, is this CIFAR-10 dataset. It consists of 60,000 colored images that are 32 by 32 pixels and are divided into sets. The one set is for learning or training. It consists of 50,000 images, and we have the other one for testing. So for each pixel, we observe 3 colors. So we have for every picture, for every pixel, three colors. The dataset consists of 10 classes. We have pictures of airplane, cars, birds, cat, deer, dog, frog, horse, sheep, and trucks. Each image is marked with a number from 0 to 1, responding to one class. So when you have a supervised learning task, you have the labels. So you know what is on the image, you know, for example, which data are like, I don't know, if you have different flowers, you know that these specifications are for, I don't know, flower called Virginica. So in supervised learning, we have labels. When we have different categories, it's good to use this one-hot encoding. When you have a number of zeros and one, in a way, how many classes you have. For example, we will have a vector from that has, for example, 9 zeros and just one in the case where is the label. So this is a binary like representation with zeros and one, and it's called one-hot encoding. We use it when we have a lot of classes. Why we are using it? Because it's easily to be to rescale it. We can like analyze for every class what is the percentage of the probability of that class to appear and similar. So this is the representation which we will use, and this is the data set that we will work on. So it's called CIFAR10, and we will load it and work with it. Okay, so this is the data, and now about the method. So we will use a convolutional neural network. Convolutional neural networks are a type of neural networks that are designed specifically for tasks of computer vision. So to work with images or some spatial data. They're like really effective in the field of computer vision for different tasks like image classification that we will do today, object detectors, image classification, not classification, but segmentation and similar. How they look like? So we have input, we have some input layer or input images in our case. We have output layers. So in the input layer, we have stored the pixels of the images that we are like giving to the network. And in the output, we have the probabilities of which class will be like more probable to be on the image. So we have input, we have the output. The output is always like of the size how many classes you have. And in the middle, we have something that is called hidden layer. So we have input layer, hidden layers, and output layers. In neural networks, you have only fully connected layers. But when you have convolutional neural network, we have also this convolution and pooling layers. What is the idea? The idea is to find some features on your image that are important and then to train your model to recognize what is in the image. We are doing this with convolution, and then with pooling, we are like just reducing the dimensionality of these obtained feature maps. How the convolution works, in the convolutional layer, we have something that is called a filter. These filters are like smaller units from our image. For example, if the image is 32 by 32 pixels, we can have filters that are of smaller size. So with the filters, we want to train the network. So we want to give them weights, and we want to from them to find when where on the pictures something interesting is like happening and similar. For example, we can have on the image a lot of filters. If we have more filters, we can recognize more features. So the more filters we have, the more features can be recognized. When you are like at the beginning of the network, like here, the network can recognize some basics, for example, shapes, some edges, some contours, some like the most basics, basic shapes like circles, squares, and similar. So you can see here like what the results are like in the second layer, like at the beginning of the network. But when you go deeper in the network, you have more convolution and other filters. It can like recognize parts of the image, like for example, the wheel of a car or the head of a dog and similar. And when it comes to the end of the network, it can recognize entirely what is in the image. For example, there is a dog, there is a truck, there is a deer, and similar. So when we perform convolution, we have these filters that go through the image, and we want to find with them some at the beginning some edges, some contour, and some circles, angles, and similar to see what we have in the image. So we want to find features that are like important for one class or the other class, so that the model knows, oh, okay, if it has these features, if the filter finds this feature, it will be a dog. This is like the idea. Every filter needs to be activated if some property appears. So if it's, for example, if a certain type of edges appear, the filter has to be activated. How we do that? We do it with activation functions. So there are a lot of activation functions that are used today, but these are like one of the most famous. We will use this ReLU, that is, if it's like bigger than 0, then it's activated. So the goal why we use activation function is to introduce some nonlinearity, because if you don't have an activation function, you have just a regression model. So this is one idea. So we have these filters that go through images. They have to be activated if they found some feature that is of interest to us. And then we will have our output. One thing that is also important is that some important information can be, for example, in the corner of the image, or at the edge. But if you go through the image with, I don't know, a filter that has 3 by 3, so this is our picture, and this is like the filter. This corner pixel will be taken into consideration just one time. And maybe we have some interesting information there. The edge pixel will be taken into consideration 3 times. And you can see that some middle pixels can be taken into consideration then 9 times. To prevent this, you can also use padding, that is adding zeros around the image so that also this corner and edge pixel can be taken into consideration for the convolution, so for the passes of the filter more times, and then it's better to find some features also that are in the corners and edges. When we do this convolution, so it's called convolution when you are going with the filters through the image, we have some results. So it's called feature maps, where we have the map of every feature that is found. This can be of big resolution, and we want to reduce this, and then we can use pooling layers to obtain smaller layers. We do it by 2 most famous methods. One is average pooling. So for example, if you have a pooling with 2 by 2 filters, you will find the average number between these 4 values, or by maximum. This is an example of maximum pooling. So you will find the maximum value, and in that way you will reduce the resolution. This is an example of max pooling with 2 by 2 filters and a stride of 2. What mean a stride? Stride is for how many pixels you move horizontally and vertically when you are doing the convolution or you are doing the pooling. So for example, in this part, so you start from here, in what is the stride, for how many pixels you will move forward with the filter to find new features. Okay, so these are the basic terms that we need to know to create a convolutional neural network. This is the architecture we will create. So we will start with an input layer, and we will have also the output layer with 10 classes, because we have 10 classes in our dataset. In between, we will have different convolutional pooling layers, also a dropout layer, then again convolutional pooling, dropout, etc. So these convolutional layers are used to extract features. But also we want to classify at the end into classes our results. For that part, we use fully connected layers that are the basic of neural networks. So for classification, we use fully connected layers, and for feature extraction, we use convolutional layer. So any network can look like this. In the hidden layers, we can have a lot of convolutional layers and pooling layers. And then at the end, we have fully connected ones. Okay, so let's go back to the script in Google Colab and try to implement this. Okay, first we have to prepare the data. I wrote you here what are the versions of TensorFlow and Keras that you need to have, but in Google Colab you have that already installed, so you don't have to do anything. And we will load the CIFAR10 dataset. You can find a lot of dataset on different places. A lot of these libraries like Keras, TensorFlow, and Skylearn and others have example dataset in their libraries, but you can find it on Kaggle, on how it's called, OpenML and similar platforms. If you use it from Keras, you can see that the data is already divided in the train and test set. So we have 50,000 images in the training set and 10,000 in the test set. We can copy from here the function that we need to load the data. So every library has its own method to load the data. When you find the library, you have to look how to upload it in the system. So we can press to run this code, and it will download the data that we need, and it will download it in this variable. So in the X train, we will have the pixels and their value, and in the Y train, we will have the labels. The same thing is for X test. We will have for the set for testing, we will have the value of every pixel, and in the Y, we will have the labels. Why we have two sets is because the thing that is called overfitting. If you learn the model and then test it and train it on on the same data. So if you like taking the data from a train set, for example, from the set, and you train on them, and then you test on that same data, you will get a good result on that part, but your model will not be able to work with some unseen data. Because of that, we are using different sets. So we have training set, we have a validation set, and we have a test set. So when we are training, we are like learning from the training set, and then after every pass through the network, we have to update the weights that are stored in the filters. So we have to test how the model is performing on some unseen data. This unseen data is called validation set. And then when we finish with the training, then we test on other unseen data that is called the test set. So we have three different sets that we are using for training and testing the model. Okay, so let's see what we have in these sets. So in xtrain.shape, we can find out what we have in this variable. So we have 50,000 images that are like 32 by 32 pixels, and they are in color. In the epsilon, we have the labels. So we have just one column with the value of the label. For example, we want to see what is in the first image. When you want to access some value of the image, we are writing that in this brackets. And every picture has its position, like index. And if you want to access it, the first image is always on 0. The second one is on 1, etc. So if you want to see the values of the first image, we are seeing that we have 3 values for every pixel. And there are numbers between 0 and 255. So this is like how it looks like. And in epsilon, we have the label. To write some text along with labels and other results, we can use a print command. And for example, print the class of the first image is, and then where is the label. So we have the label 6 for that. We can add here class names and similar, and then write that is a frog, but we will do it later. Okay, Google Colab has now that you can like show the image, but let's try with another library. So matplot library, pyplot function is widely used to show images. You can make some subplots inside and similar. We can try first to show the first image and then to show the first 5 images. So the command is imshow. And we access like the first one with the index 0. So it looks like this. We have 32 by 32 pixels that we can see here. Okay. So this is how we show one image. If we want to show a range of them, for example, from the first one to the 5th one, we go from 0 to 5, and we can make some subplots. So for example, that we have 1 row, 5 columns, and then visualize all of them. So it's the same thing. So xtrain, but it's not just from the first image, but we want to change that value every time that you like change also the position. So we have this for loop for that, where we change the value of this E representing the index inside the X train. After that, if we run it, we will obtain the first 5 images in the training set. Okay, so we have to use, when we have a lot of categories and they're like written with different symbols, names and stuff, we want to use this one-hot encoding. So we want to do is to obtain zeros and 1 where the class is. We have a function to do that. It's called toCategorical. So we want to change the variable. Sorry, we want to change this variable epsilon train to have now the one-hot encoding. We can use a function that is written to do that. It's from Keras utils. It's called toCategorical. What we want to change epsilon train, and we have to put the number of classes that we will have. In our case is 10. Everything that you do on a training set, you have to do the same thing on the test set. So you can copy this command and change it. So we can see that we have now zeros and 1 where we have that class. Okay. One thing is left to do to prepare our data. This thing is called data normalization. So we want to have data between 0 and 1, and we have images that contain values from 0 to 255. So our model will have better performance, it will run faster, and similar if we have values between 0 and 1 and not a really big range of value. Data normalization is important step, but is not required in every case. So in this one where we are like working with images, it's okay to normalize data. In some other, maybe it's more important to obtain real values and similar. Okay, so to do this, we can just easily divide by the maximum value is 255. What we do on the train set, we have to do it also on the test set. Now, if we look at the first picture, we have now values between 0 and 1 in our data set. Okay, now we have prepared the data. We have normalized it. We have divided it in training and testing set. We have seen the data. We have also the labels in one hot encoding. So we are like ready to do our network. So this is the architecture that we will create. It's the same one that I showed before in the presentation. So first we will create two convolutional layers, then a polling layer, and then dropout layer and other. First, you have to define how the model would look like. And write the name of the model. So you can name it how you want. I will name it model. And you have to define that it will be a sequential one, which means that you will add layer after layer. So from keras.models, we will take a sequential one. In this part, is important that you don't run multiple times the adding of the layers, because every time you like run the code, you will add more layers to it. Then once you like write everything, you can run it again from this line if you want. Okay, so we defined the model, and after that we are ready to add the layers. So it's really easy to add. So you write model dot the name of the model dot add, and then you find the layers that you need to use. So from keras dot layers, you will have a list of different layers that you can add. For example, we will use this convolutional 2D because we are working with images. You can use LSTMs, you can use dense, you can use dropout layer, flatten layer. So there's a lot of layers that are available here. So the first one is our first convolutional one. So we are writing conv 2D. We have then how many filters we will have. This is the depth, 32. And what is the size of the filters? So we will have 32 filters, and the kernel size, so the size of the filter, will be 3 by 3. The next variable that we need, the next argument that we need to do is the stride. By default is 1, so every filter move through the image for 1 pixel horizontally. When you come to the end of the pictures, move for 1 vertically. So we don't have to write this because this is like the thing that we want is y by 1. we have to write the activation function. The one that we will use is called relu. And if we want to take into consideration the pixels at the edges and at the corners, we have to change this padding from valid to same. So if it's valid, it's without it. If you put same, then he will add zeros around. Every time that you define the first layer of the network, you have to define the input to the network, the input shape. So the input shape will be 32 by 32 pixels, and we have colored image, so 32 by 32 by 3. So the input shape you have to define only in the first layer. In every other layer, the network do it automatically. Okay, after that, we have another convolutional layer that is the same like the first one. So you can copy this part. But the difference is here that we are not writing the input shape. It will be calculated. After that, we have a max pooling layer. So to reduce the feature maps, I will copy this part. So we are adding now a max pooling. Also 2D because we have pictures. And we have to define the pool size of the filter. Okay, by default is 2 by 2, but we can write it down so you don't forget what we did here. So we want to go through the feature maps and reduce the dimensionality by using maximum pooling. Okay, after that, we have here dropout layer with dropout probability of 0.25. What that's mean? So in each pass during training, a certain percentage of neuron will be discarded in order to be less sensitive to some changes in the input data, and in this way prevent some overfitting. So when you are like, think of that some part of the image will be missing, and then the networks learn to so some pixel will be missing, and the networks learn to be more less, sorry, it will be less sensitive to some changes because I don't know, some pixel will be missing, and then it will be easier to recognize something that is not identical. Because of that, we are like using this dropout layer. So it's to prevent overfitting and the network to be less sensitive to some changes in the images. Okay. I'm missing one. here. So we are adding a dropout layer now. So drop out. And we are like, we can write the rate. So between 0 and 1 is the percentage of how many pixels we want to not take into consideration. We can look like that. Okay, then we have two convolutional layers. So we can copy this one. But we have 64 by 64, so we'll, no 64, we have 64 filters. So we will just change that part. After that, we have again a max pooling layer. After that, we have again a dropout layer. Okay, this is the part that we know how to do. And then you see that we have this fully connected layers. So in the fully connected layers, every neuron is connected to another one. Just a second. So this is how it looks like. So in the input layer, we have the value of every pixel. And then we are like connecting it to the neurons that we are like working with. Okay. To do so, we have to flatten the input. So that is one vector with every feature that we have, with value for every pixel that we have. We are doing this with the layer called flatten. So it only changes the dimensionality of our network. So dot layers dot flatten. And after that, so every time you want to add fully connected layers, this have to be before that. And now we can add this fully connected one. They're called dense. We define how many neurons we want to have and what is our activation function. So we have this one. After that, we have a dropout layer. Of 0.5. And the last one, that is also a dense one, fully connected. But here, the number of neurons is equal to the number of classes that you have. So if you have 100 of classes, you will write here 100. In our case, we have 10 classes, so we'll write 10. And now the activation function is not relu. For the classification, the activation function that we used is called softmax. I don't have it here. So it looks like this. Okay, with this, we finish creating our model from scratch and we can run the code. So one by one, just press one time. So if you press more time, you will just add more layers that we want. And this is like the final thing, we like created the model. We can check the architecture of the model, so how it looks like by model.summary. Okay, I will wait a few minutes. Okay, so let's go to the important part. So we want to train the model. For training the model, first we have to define what we are like following, how we are like compiling the model, how we will optimize these weights in our network. We do it with a function called compile. So we write the name of our model dot compile, and then we have to define first the loss function that we will use. So loss equals to, when you have, for example, a binary problem, you will use, for example, binary cross entropy. When you have categories, you will use categorical cross entropy. So you have to see what is your problem and which loss function will be adequate for your case. So we have categories, so we will use categorical cross entropy. Then we define how we will optimize our model. So you have different methods for that. Two that are most common is stochastic gradient descent and Adam optimizer. You can try what you want. Here is not so important. Both works great on this case. So we define the optimizer. Adam, and at the end we define what we want to monitor. For example, accuracy is like the most important in. So you are like looking at the accuracy and at the loss at the same time to see how you are performing, how your model is performing. So you define the metrics. You can now here allocate more of them, but for us is enough the accuracy. And now the last thing is to train the model. When we train the model, we have to define a few things. First, what is the data for training? So we have the data with the pixels, and we have the data with the labels. So this is like the first thing. After that, we have to define the batch size. This is the number of training data used during one iteration. So it's the sample on which we work before updating the model. So we want to, when we are training the model, we are like validating it on some data that it haven't seen. And then, for example, in the first step, he predicts that this is a deer. It's not a deer, it's a cat. Then we are like saying to him, okay, you got that wrong. It's a cat. Can you correct that? And then he in the next steps corrects that part, and we have a lot of iteration of that. So the batch size is the number of training data during one iteration of that correction, but you don't have to take every pictures in that part. So the batch size is the number of training data that we are like taking in one iteration, and a lot of iterations are like one epoch. The epoch is when we like pass through all the data that we have. So if we have 60,000 images, one epoch will be when you pass all these images in the training set. But we can update after 32 pictures, for example. So this is like the batch size. It can be more or equal to 1 or less than equal to the number of samples that we have in the training set. Number of epoch that you will be training is up to you. So you define this number. It can be integer number between 1 and infinity. So, but also it's not good to train, I don't know, for 200 epochs because you will overfit your model to only get familiar with the data you are using. If you define you want to perform the model train the model for example, 20 epochs, you can also define a callback. That is, if the loss isn't like better, then stop training. So this is also one thing that you can do. So you can put, I don't know, 100 epochs to train, but if the loss is not improving, then stop training. So this is also the part that you can do. Okay, so here's also what is the difference beside epoch and batch. If you have a dataset with 200 samples and you choose a batch of 5 and 100 epochs, these mean that this dataset will be divided in 40 batches, each with 5 samples. So after every 5 samples, the weights will be uploaded. Okay, so the function to train a model is called fit, but we will save this value in one variable just to visualize after what we have. So first, what we have to define is the data that we are using to train the model. The data are in X and X train and Y train 1 hot. So the first one is X train. Then we have the label epsilon train 1 hot. We can define the batch size that we want. So we want to take 32 images. We want to train, for example, epochs for 10 epochs. And one thing that we have also to define is the validation set. So if you have like divided it before, you will write validation data equals to, and then the sets that you will use. If not, you can take a part of the training set for the validation, and then you are writing validation. So you can use this validation data if you have defined the data before. If not, we are using validation split. And we are like taking 20% of the data from training to validate the performance. Okay, once you define it, you can click on here and our training will start. I hope everybody changed to GPUs. If not, it will be a problem. Okay, so in the first epoch, we have, this is like the loss that is on the training set. And this is the accuracy, what we have is 42%. This is on the same data that is training on. So this is on the train set. Once you have finished with this on the training set, it tests on the validation set. And that's the part when we want to have high results because these are unseen data. You can see that after each epoch of training, the accuracy increases and that the loss is being smaller. The results will be even better, I think, if we like train more, but for this example, it will be fine. Okay, I hope it doesn't break. I don't know what is the problem now. It should finish by now. Okay. And now we can visualize the accuracy and loss. So you can see here, the accuracy can be from 0 to 1. Because of that, we have like these values. And we see how by training, the accuracy increases. I think if we like will train more, we could have better results. I hope this is working for everybody. Okay. If you want to save the model and then access it later, you can use this model.save and then write the name how you want to save it, .keras. Once you save it, it's here and you can downloaded it, but also you can like save it directly to your drive, then you don't have to do that part. Okay, so now we have to test the model. We are like testing the model on the test set, so on unseen data. The function for that is called evaluate. So we are like giving to evaluate the results of predicting the classes in the test set, but look at the labels, how good it is performing. When we, sorry, it's test here. So here we obtain the loss of 0.72 and the accuracy on unseen data of 75%. If you want to have the predictions for every pictures, you have to use the function predict, and we want predict for the test set. If you want to see the prediction, for example, for the first one, for the first image, we have values between 0 and 1 for every class. What is the probability of this class being a frog, a deer, this image being a frog, a deer, and similar? We want to take the highest one to be the final prediction. Just run this class name so we don't have just 0, 1, 2, 3, but we can see the differences between them. One useful metric is this classification report because you have everything inside it. So you have precision, you have recall, you have accuracy, all in one place. So when you are like doing precision or recall or this classification report, you have to write on which data you want to have the results. So it's written here. So first we write the true value and then we write the predicted value. So the true value is in epsilon test, and the predicted is in epsilon red. And we want to target names to be these class names that we defined here. When we run it, we can see the precision for every class, the recall for every class. We also have the F1 score that combines the precision and recall. We can see how many data was in each of that class. And we have the accuracy on this testing set. So this is what we can plot. The same thing we have for the confusion matrix. So the confusion matrix show us where was the confusion, what was wrongly classified. So we can see in the results, for example, what was what was the like main mistake and similar. For example, this is one is I think the highest. It's between the dog and a cat. But if you look like we have airplane, out cars and similar, it's like reasonable that it has that mistakes. So this matrix helps you to see what was the true label and what was the predicted one, and then analyze where the model is having trouble and if you can like improve that in some way. Let's test it on our image. This is a system command that takes an image from a link, and I call it the cat picture. What is important, if you are like testing other pictures, you have to resize it into the dimensions that the network is taking. So we have to put it in 32 by 32 pixels. And then we have this image of a cat. And we want to find the probabilities. So we are predicting on the cat what will be the probabilities for every class. We want to sort that probabilities and then to visualize, for example, how the model is sure that there is some class in the picture. So how to interpret this? We have a probability that a cat is on the picture with of 58%, then that deer is on the picture around 20%, the dog is in the picture 11%, and other. So this is like the first 4 probabilities for the pictures. In this case, we just took the highest one, index of the highest value, and then make the confusion matrix of that. And in this case, we like wanted to see for this concrete image what are the probabilities. So this is like the part that it was planned for this tutorial, but I added some more things that I hope we will have time to pass. So this was the creating a convolutional neural network from scratch, but you have a lot of models that are available online and they're free to use. So you can use different pre-trained models and then fine-tune them for your case. For example, there are a lot of, for example, model zoo is called, when you can find different models of TensorFlow, of PyTorch, and similar. We will use from the library of Keras that also has inside different models like MobileNet, EfficientNet, and similar. We will use ResNet from it. So we have to import it. And why we want to do that? Because this model are like trained on really big data sets, and they have learned how to extract some important features. In this part, you want reuse them and maybe fine-tune them to learn more features from your case, but to use their weights that they have learned before. So first of all, we will import the libraries that we need, and then we will look at our data. So we will also use the CIFAR dataset, but because this is like a bigger network, we will use just a part of the training set to work on, because we will run out of memory if not. So the first thing that we have is to take our data and resize them on the size that the network expects to have like for input. The ResNet expects 224 by 224, the dimension of the image, and we have only 32 by 32. Now, the first step that we have to do is to resize our images to the size that match the network you want to use. So first, we want to resize it. So X train. We can use some function to resize. For example, from TensorFlow image.resize. We want to resize the X train. How we want to resize it to have 224 pixels. Every network has also some data processing for the input data, and you can find this function preprocess input. So we have to preprocess our input before giving it to the network. So Xtrain equals to preprocess input. We don't have time, so we'll not test it on a test set, but everything that you do on the train set, you have to do also on the testing set. So you will also resize the the test set. You will also pre-process the training set, and you will also convert it into one-hot encoding when you will run the testing. Okay, and we have the one-hot encoding like before. So epsilon train, it's already imported, so just to categorical. Epsilon train, we have 10 images. Okay, we can run this part. And now we can take the ResNet model. So we are using transfer learning. So we want to remove the classification layer because we have different number of classes. In the ResNet, they have pre-trained weights from the ImageNet, where we have 1,000 classes, and in our case, we have only 10. So we have to remove the top layer that is for classification and adjust the model to fit our problem with 10 classes. Also, we want to freeze the weights. So we have the weights that are pre-trained on the ImageNet, and then we want to train additionally to extract some features from our data. So let's try that part. We can call it first the base model. So this is like this ResNet that we are starting with. We have to define the weights that we will use. From the dataset ImageNet. Do we want to include the classification layer, so the top layer? We don't want it. We don't want that because we don't have the same number of classes. So include top will be false. And this will be our first layer, so we have to define the input shape. We have to freeze these weights. So the base model dot trainable, it will be false. We have to create the model like before. So model 2, we can name it models dot sequential. And we are adding our layers like before. So first we are like adding the base model. After that, we have to add a pooling layer, but this is another one. It's called global, because when we use another model that we don't know how everything looks like, is better to use this one. So global average pooling, not 1D but 2D. And after that, we can add the final layers for classification, the fully connected ones. How many neurons we will have, for example, 1024. The activation function will be relu, and then one more layer, model 2.add layers dot dense. We will have the number of our classes, and the activation will be softmax for classification. Then we just define the compiled part and how we will train it. Let's try that. And after that, we can visualize, and then you can, on your own, trying to test the data to see the confusion metrics and everything of it. So you can see that even in the first step and with a lot less data, so with less data, we have only 2,000 images, we are obtaining higher results. You can then evaluate on the testing data. So this is like, we had one example of creating the convolutional neural network from scratch. And this is another one when we are like using pre-trained models and then fine-tune them to be good for our case. So we have here the results. We can see that the accuracy on the training set is really high, and that the validation accuracy is also 86% with only 2,000 images. So we have better performances than from this one that we trained from scratch. Okay, so this is it. I hope you learned something new. I will put the script after we finish with all the codes if somebody didn't write something. And I think that's it.